Hello everyone, my name is Eric, and today I'm going to tell you about a static analysis we built for probabilistic programming with streams. The analysis will tell you if your program will execute in bounded memory when inference is performed with delayed sampling. So in probabilistic programming, developers write down using code a specification of a probabilistic model. For example, this little piece of code specifies what is known as a Kalman filter. It is then the job of the inference engine to perform Bayesian inference. And what I mean by Bayesian inference is the inference engine takes in observation inputs, which are values, and produces a distribution that is conditioned on these values. Bayesian inference is in general hard, and as a result, inference engines can be quite complex. Particularly interesting for our purposes is that because inference engines are complex, their memory consumption properties can be quite complicated. In a streaming context, probabilistic programming happens at each time step. So at each time step, we take an observation input, pass it to the inference engine, and get a distribution output that is conditioned on this observation. And in future time steps, we also do this with the added detail that there is some program state that is passed around from time step to time step. And in general, in a streaming context, the number of time steps can be very large or even infinite. A particular property that we're interested in a streaming context is bounded memory. That is, even though a program is executing for a potentially infinite number of time steps, it should have a finite memory footprint. Conversely, if a program allocates more and more memory as it executes for longer and longer, it would eventually run out of memory and crash the computer. So that would be bad. So to discuss this in more detail, I want to be more concrete about a specific inference technique. So we're going to talk about delayed sampling. So I'm going to run through how delayed sampling works on this Kalman filter example. And this Kalman filter example specifies some initial state and then specifies a step function, which is what the inference engine is supposed to do at each time step. So the way that delayed sampling works is it specifies a non-standard interpretation for these sample and observe constructs. And in particular, delayed sampling uses this graphical model-like data structure called the delayed sampling graph, in which nodes of the graph are random variables. So if we execute the step function, we say let x equals sample a Gaussian distribution. What delayed sampling will do is it will create a new random variable node, x0, and return a pointer to that node to be stored in x. I've drawn this pointer as a dashed line on this diagram. Similarly, when we sample y, delayed sampling will create a node y0 and return a pointer to y. And now we're going to make this observation. So we're going to observe that y is equal to the observation input obs. And this is going to be an internal state change operation for the delayed sampling graph. And in particular, I want you to notice that the direction of the pointer between x0 and y0, which is internal to the delayed sampling graph, the direction of that pointer has flipped. All right, so at future time steps, this particular program specifies that the variable pre-x is the program state, and it always refers to the previous value of x. So in delayed sampling, what this means is it refers to this node x0, because that was the previously sampled value of x. So at the next time step, we're going to execute the step function again. We're going to sample x again. We're going to sample y again. And we're also going to observe y again. So this is going to perform similar operations to what happened at the first time step. And then moving on to the time step t equals 2. Again, pre-x is going to be the previously sampled value of x, which is now x1. And we're going to continue on sampling x and y and observing. And we're going to continue on like this at future time steps. So one thing to note here is that the size of the delayed sampling graph for this particular example is going to be infinite if as time becomes infinite. And so this is a problem for running in bounded memory. If we want to have any hope of running in bounded memory, we have to somehow bound the size of the delayed sampling graph. So how can we do this? So what we showed in some prior work is that we can make use of the fact that not all of the nodes in the graph are reachable. So what do I mean by reachable? What I mean by reachable is if we start from every variable that is in the program state and follow the transitive closure of all the pointers, that's the reachable set of nodes, and the remaining nodes are unreachable. So in this case, only x2 and y2 are reachable, the rest are not reachable. And if the nodes are not reachable, they cannot influence the computation of future time steps, and so they can be safely garbage collected away. And so in this way, if the set of reachable nodes is always finite, we can execute in bounded memory even with an infinite number of time steps. However, This property of bounded memory is a program-dependent property. So I've gone ahead and modified this column filter example to this new program on the right. I don't expect you to read this new program. I just want to note that I have changed the program state here. Whereas previously we just had this pre-x variable, now we also have this variable I. And what I is ultimately going to do is it's going to hold on to the x variable that we sampled at the initial time step, so x0. And it turns out that if you do this, it results in this program not executing in bounded memory. So this raises the question, can we somehow determine if a given program is going to run in bounded memory when inference is performed with delayed sampling? In this work, we show that the answer to this question is yes. In particular, I'm going to talk about two semantic properties, the mconsume property and the unseparated paths property, and taken together, these properties form a necessary and sufficient condition for a program to run in bounded memory under delayed sampling. We have also leveraged these semantic properties to build a static analysis, and I'm going to talk some more about the results we obtained with this static analysis and give some concluding remarks. Okay, so let's talk about these semantic properties. So the way we formalize these is with respect to traces of these streaming probabilistic programs. And what I mean is as we're going through executing the probabilistic program, we're going to record all the operations that we're doing. And this record that I'm showing on the right is the trace, and that's how we are going to model the execution of this program. That's how we're going to define these properties. So some things to note about the trace. So it only contains data flow information. So it just says x0 was sampled, y0 was sampled from x0. It doesn't know about the values or the distributions that are involved here. All right, so the mconsume property. So first I'm going to define what mconsume means. So a variable is zero consumed if it is directly observed. So for example, y0 is zero consumed. A variable can also be mconsumed if it is passed to another variable, that is another variable is sampled from it, and this other variable is m-1 consumed. So x0 is 1 consumed because y0 is sampled from x0 and y0 is 0 consumed. The mconsume property states that there must exist an m such that every variable introduced in the trace is m-consumed. So for example, in this trace, we can maintain that every variable is 1 consumed. All right, so what could happen if we fail the mconsume property? So say we took this column filter, which as we saw satisfies the property, and removed this observe statement. So let's look at what happens now to both the trace and to the delayed sampling graph. So as we execute this program, there's two things to note. So one is that all the observations have been removed from the trace. And the second thing is that this pointer flip operation that I described earlier no longer happens because we've removed the observe statement. So this means two things. So first of all, this program is going to fail the mconsume property because y0 is not mconsumed, which means x0 is not mconsumed. None of these variables are mconsumed. So it's going to blatantly fail the property. The second thing to notice is that if we look at the delayed sampling graph, so pre-x is holding on to a pointer to the most recently sampled x variable, and this x variable is holding on to a pointer to the previous x variable. And in general, this is going to keep alive all of the x variables. They're all going to be in the reachable set. And so the only ones we can exclude from the reachable set are the y variables. And so this is going to result in an unbounded number of reachable nodes as time becomes large. And so this is going to result in an unbounded delayed sampling graph and ultimately unbounded memory consumption. All right, let's look at the unseparated paths property. So first I'm going to explain what an unseparated path is. So an unseparated path is a sequence of variables, each sample from the previous one such that no variable is directly observed. So for example, in this program, we have an unseparated path that goes from x0 through to x1 and then through to x2. And this unseparated path must have length at least 2 because that's how many variables are involved. The unseparated paths property states that there must exist an n such that at any time step, no variable that is in the program state at that time step starts an unseparated path longer than n. So if we look at this example, the program state at each time step consists of the most recently sampled x variable. So by the time that we get to the part of the trace where x2 is introduced, At this point, x0 is not in the program state anymore. And so what this means is that this particular path is not going to count for the purposes of the unseparated paths property. And in fact, this trace will maintain that the longest unseparated path that starts from a program state variable has length at most 1. So what could happen if we failed the unseparated paths property? So if we look at this Kalman filter example, and I'm going to modify it in the same way that I did earlier, which is that we're going to have this I variable that holds on to the very first x variable that we sampled. So what's going to happen here is that because I holds on to x0, and transitively x0 holds on to all the other x's, which transitively hold on to all the other y's, the whole delayed sampling graph is going to be inside the reachable set. And so because the delayed sampling graph becomes infinite, as time becomes infinite, the delayed sampling graph is going to be unbounded, and therefore memory is going to be unbounded. Correspondingly, because this I is now in the program state, it means that at every time step we're going to have x0 inside the program state. And so because of this unseparated path is actually going to be valid for the purposes of the property. And because this unseparated path is going to get longer and longer as the trace becomes longer and longer, we're going to fail the unseparated paths property. Okay. So in the paper, we have some more extended formal development, and we also have a proof of this theorem, which says that a program satisfies both semantic properties if and only if it executes in bounded memory. So we have also leveraged these semantic properties to build an analysis, and we've done this by coming up with abstractions of both the program state and the delayed sampling graph that are sufficient to show that a program satisfies these semantic properties. And I don't want to go too much into the detail, except that I do want to mention that we have a theorem that says that if the program passes the static analysis, it satisfies the semantic properties. So this is stating that our analysis is sound. And we have more details on the formal development in the paper, and we have a proof in the appendix. There is also an implementation available online. And so because we've proven the analysis is sound, the remaining thing to evaluate empirically is how precise it is. So to do this, we ran it on a number of benchmarks, and for each benchmark, we ran the analysis and saw what it said, and then we compared this against manually reasoning about each benchmark, manually reasoning about whether or not it satisfied each property. So for the first 6 benchmarks, we found that the analysis is precise in that it exactly describes whether or not a program satisfies the given semantic property. The remaining 2 benchmarks are an interesting case. So the analysis says that these fail the mconsume property. And in fact, these benchmarks both have executions that do exhibit unbounded memory. However, because these benchmarks are probabilistic, it turns out that these executions happen with probability 0. So with respect to the formal development in this work, we say that the analysis is precise because it tells us that these bad executions exist. But it might be an interesting direction in the future to look at. Maybe the memory is bounded in expectation, or we have strong tail bounds on the amount of memory consumption. So yeah, that might be an interesting direction for future work. And then finally, we have this example where the analysis says that memory could be unbounded, but in fact, it actually does run in bounded memory. And I'm not going to have time to go into the details on this, but if you want to talk more about it, I'd be happy to talk offline. It is kind of interesting. All right, so to summarize, we talked about the mconsume property, the unseparated paths property, and I briefly explained how we leverage these to build a static analysis that can tell you whether or not your program runs in bounded memory. There's 2 important takeaways from this. The first thing is I think we need to really think about when we're running our probabilistic programs how they're going to perform with the inference engine that we're using to perform inference in. So I think it would be really interesting to think of other program analysis problems that might be able to do similar sort of things for different types of inference engines that are maybe not delayed sampling based. The second thing I want you to take away is that this is an important step on the road to making probabilistic programming with streams practical. In a streaming context, it's really unacceptable to have unbounded memory behavior. And so with our static analysis, developers can rest easy that if their program passes the analysis, then their program will run in bounded memory and will not exhibit this bad behavior.